For the last talk of this afternoon session, it's my pleasure to introduce MD Aquib Molla from Vidyasagar College, who will tell us about heartbeats and flow, exploring percolation theory in cardiac cells.
Good evening, everyone. First of all, I would like to thank the organizer to give me the opportunity to present my talk here. Today, I will be talking about heartbeats and flow exploring percolation theory in cardiac cells. This work is mainly done by me and my supervisor, Dr. Sanjay at Vidyasagar College. We begin by understanding why this topic is so important. When electrical signal moves in heart-like cells, and the action potential shows malfunctions due to transmission, this leads to serious heart diseases like tachycardia and arrhythmia, where the heart rhythm shows irregularities and even faster than usual. This can cause strokes, heart attacks, and even death. So by understanding how the signal propagates through such system, we get to realize that how to deal with these diseases and maybe possibly find some solutions too. So there are types of percolations like directed percolations when only forward direction is allowed and backward any other directions are forbidden. For examples, forest fire model, academic spread, or maybe information flow in media, even rumors too. In case of isotropic percolations, when all directions are allowed here, and for examples, network connectivity and electrical signals through neurons. For our model, we actually deal with electrical signals, so that is why we chose isotropic percolations. And as Rup said that this bond percolation, he discussed bond percolation, we will discuss side percolations here. In our model, we chose heart as a 2D sheet and L cross L grid, and each cell corresponds, each grid actually corresponds to a cell, and we categorize 3 types of cells. First one is active cell, which contains the action potential, and the second one is waiting cell, it actually waits to get the action potential from neighboring active cell. And there are some transformation rule, I will come to that later. And the third one is inactive cell. It's quite similar to a dead cell. I mean, even if there is a neighboring active cell, it will not take the action potential at all. And initially we start with a initial distribution of waiting and active, with waiting probability P, and it will be 1 minus P with inactive. And set the action potential on the one side in case first row action potential. We chose this color to be green, yellow, red because when action like active cell, which actually contains the action potential, means it's always ready to go. But in case of waiting, it actually waits to get the action potential. That's it's quite similar to the traffic signal, and red means it's blocking it. And in addition to that, we also set 2 parameters here. One is P act and another is P switch. That's a transformation rule that whenever a waiting cell in each Monte Carlo step actually, whenever a waiting cell sees an active cell, it will transform to active cell with a probability P act. Suppose P act is 1, that means the system is 100% efficient to take the action potential from other cells. And if we reduce the P act value, it's kind of, we are introducing some inhibition into our system. Like it's not generating with 100% efficiency. But, and the second one is P switch. That is, it's quite similar in case of forest fire model, growing of trees from random site, which actually, in that site, suppose the tree has already burned. Now the tree is growing. In our case, it's like a cell, dead cell, trying to recover to its original state. And along with that, we also have another conditions that in each Monte Carlo step, an active cell will convert to an inactive cell. It actually loses its action potential. Here's the simulation. We run a simulation for 10 cross 10D 10 cross 10 grid and setting P act to be 1 and P switch to be 0. That means whenever a yellow cell sees an green cell in the next Monte Carlo step, it will convert to an active cell with 100% efficiency, no question about it. And P switch to be 0, that means if a cell is dead, it remains dead in that condition, no matter how long you actually try to study. This is the condition of t equal to 0. We initialize this system in this condition, and this is t equal to 1, 2, 3, 4, and finally this system looks like that. We also calculate how many green cells comes at the bottom. That is, it's quite like we generate a signal and trying to receive the signal from other. Sure.
Sorry, I think I missed something. You go from yellow to green, and
yes,
from.
Oh, sure.
So why on the second row here they didn't become green?
Second row become green. These are the yellow cells. This takes the action potential from here, neighboring active action potential, because the P act is 1, and this also takes the action potential from here. This also takes from action potential to that. That is why the first row, this one, only become green.
But at some point it seemed that it went all red.
Oh, that one. This one become red.
In the next step.
Yeah, in the next step, this one become red. Is that your question?
Oh, it always becomes red immediately after it's active?
Yeah. When it's active, in the next Monte Carlo step, it will lose its action potential. Okay. That's it. Yeah, sure.
Go slowly through that example. Okay, this step we understand.
This one. It's also neighboring takes the action potential. Okay. And this one too.
But why did that green cell not go down? I'm a bit confused.
Oh, sorry. There's neighboring active cell is this one and this one, not this one.
Not that one, I see. Okay, so that...
Because only neighboring interactions is happening. That is why each cell has four neighbors.
Okay.
Not 6.
Right, okay, I understand. Okay. Then can you please go?
Sure.
Okay.
This one.
Okay.
And the final one, this one.
No, but what final? I mean that
green
thing will go down all the way, look.
Yeah, it will go down all the way, and finally we actually catch from the bottom. And that's why we study that number in the next slides.
That number, but you know, this is misleading. It looks like everything died, but actually
actually you can see that these green cells will active this one, this two, and then next step this one, next step this one.
Yeah, so that green cell will go all the way, right?
Yeah, it goes all the way down.
Okay,
and that's the
you said it, I thought you were saying everything just died.
No. Only these cells are remained isolated from other side. That is why these two change. It doesn't change at all. And we study this how many green cells comes from the bottom, and that is our number of arrivals. This one, any. For this case, these two figures, we set L equals 200 cross 200 grid. So first one is P switch to be set. We set P switch to be 0. There is no recovery at all. Once it is dead, it's dead. And the violet curve shows P act to be 1. That means it's 100% efficient, just like the before one. And it shows a Gaussian nature. I mean, the signal, of course, since it is 200 cross 200, so it at least take 200 time step. So after 200, it comes up and dies down. Within 300, the signal completely passes. I mean, it's 0. And if we incorporate inhibition, that is reducing P act value, then we are actually incorporating more inhibitions into our system. So we can see that the peak height reduces. Because in this case, you are not getting lots of active cells. I mean, generation of active cells are reduced. So that is why the peak height also reduced. And the peak position moves towards right. This is because in case of the first one, the active cell take the shortest path. Now, in case of this, if we introduce inhibitions, now they might have taken the longer route. So that is why the delay arises. In the figure 2, we set P switch we set P-act to be 1, that is it's 100% efficient, there is no inhibition at all, and we play with the P-switch. The violet one here is here. By comparing these two figures, you can see that the strength of this signal is improved much better. It's good. I mean, better medications may lead this, but having very high value of P-switch is not good. I mean, making the recovery, I'm talking about it. It shows the oscillatory behavior here, especially it's very prominent for 0.9. In case of porous media, when a fluid moves, it feels a fluid shear. And in case of electrical signal, this also feels some, this must feel some retardation. That is why this nature, we are having this nature. And the most important thing is that it shows a non-zero saturation value. That means the system always traps some action potential. Basically some active cells. In this case, it's 0. It dies down to 0. But in this case, it's not 0. That means it always traps some active cells. And these active cells leads to the irregularities, because in the first slide, the heartbeat looks very prominent. It's regular. But in this case, this triggers the signal. This non-zero value. This triggers the signal, and then the irregularity occurs. We study fraction of percolating path, that is Pn. We study with a p-value, initial distributions of weighting and inactive. And for P-act 1 and P-switch 0, this critical value is around 0.59, which actually actually close to the original value and standard value. It's 0.59. But in case of the middle one, we introduce inhibition, that is P-act is 0.8. So now the PC value shifts towards right. It's around 0.72. Because now since the generation of active cells is reduced, so that is why it also trying to compensate the effect. So for that, we need to have more waiting cell to compensate that. So that is why it's 0.72. And setting P-act 1 and slightly increase P-switch, I mean only 3%. This rapidly drops down towards 0. In this case, it's 0.12. I mean this value is 1.12. I mean it's rapidly drops down to 0. That is immediately all cells going to percolate. In the insets, we have shown the data collapse also. Here's the snapshots of our system. The first one is P-act 1 and P-switch 0. In this case, PC value is 0.59. We set just below 0.59. And we can see that there isn't any percolating state. The cluster of inactive cells are finite here. But we just increase P value to just PC, and suddenly the system becomes a large blob of inactive cell and infinite clusters are formed. And if we introduce P-act in the same model, and even if we increase P value 0.7, here is 0.59, it's 70%, still we are not getting any percolating state since the inhibitions is occurred here. But in the same thing, if we set P-act to be 1, even more efficient, and setting P-switch to be 0.1, it becomes a percolating state. Along with that, I don't know whether you can see that blue dots here, these are the active cells here. I mean, they are traps inside it. Even if we take a longer time to study this system, still the active cells are within this system. And these are the reason why it triggers the signal, and making the irregularity and causing the disease. We study the largest cluster size of inactive cells and plot with L value, and find the fractal dimensions as around 1.84 or 811. And these are the cluster distributions of the inactive cell. In both cases, we set P-switch to be 0, and this is the first one, and this is the 0.9 case. In this case, cluster system size is 500, and this follows the relation equation 2, and near criticality this S max blows up. So this goes to S to the minus delta, and delta is the Fisher exponent. For this one is 1.964 and it's 1.911. We study these parameters also. It's P infinity weightage of the weight factor of percolating cluster, and this is the mean cluster size, cutoff cluster size, and all of them actually occurs after the criticality. So that is why P minus PC goes to the power this. Using these parameters, we actually calculate these critical exponents alpha, beta, gamma, and sigma by using these graphs. We plot this, and after plotting this, we are getting the beta value is 2.859, gamma is 0.6, and sigma is this 0.377, which actually approximately satisfies this relation. And there is a tabular form of all these exponents, critical exponents we get, and using this exponent, we can actually satisfy the Rasbrock inequality. In our model, it provides the better understanding how this action potential moves through heart-like system using percolation theory. And this approach may be very useful for developing better heart models, and maybe leads to some better treatments also. And thank you for your undivided attention.
Thank you. Are there any questions for the speaker?
So did you do any approximation or calculation, or is it all simulation?
It's a simulation. It's purely simulation.
Thank you. I must say I'm a bit confused by the conclusion.
Okay.
You did simulations, and I understand the result of the simulations, but do you have any, I mean, if you're talking or thinking of applications, for example,
we are actually trying to model that disease, that's it. I mean,
yes,
it's a purely statistical model, that's it.
What is the equivalent experimental data for these clusters that you showed? What would you compare to?
Sorry, I didn't follow.
In the last few slides, you showed these clusters of active and inactive cells, but is there any experimental data that you can compare with?
In case of disease like arrhythmia, the signal, I mean, it actually is the SA nodes creates the signal, which actually beats, making the beats, and when a person actually a diseased person, he in his case he actually creates the signal more than usual, and it's not regular. It shows irregularity, and using this simple model, we can actually show why this irregularity comes. That's it. I mean, we are just modeling this disease. That's it.
Okay, maybe we should talk. Obviously,
he's asking if you compared your numbers with data.
No. We are trying to model the signal.
But when you model, it has to compare to reality, no?
It's purely simplistic model. I mean, we have to do more.
Because in my understanding, the pacemaker cells that make the heart beat, they have an automatic regeneration of the potential inside through osmosis, through the membrane.
Yes.
And that is completely missing in the model. So I was lost from the beginning.
The model is very simple. I mean, simplistic thing. I mean.
Further questions? If not, let's thank the speaker again.
Thank you.